Hello class, this is Professor Feynman. So now we're going to start the section module 6 of the Regression for Science and Engineers course. And we're going to continue on with our discussion of the goodness of fit tests. And so in this module we'll do several different goodness of fit tests. And so lecture 6.1 will be the coefficient of determination, or many of you will recognize this variable as, this test as called R squared, or R squared value. And so let's begin. And I highly recommend that all of you, either before this lecture or after the lecture, to read this paper by J.A. Cornell and R.D. Berger, Factors that Influence the Value of the Coefficient of Determination in Simple Linear and Nonlinear Regression Models. And this is from Phytopathology Journal, which phyto meaning plant, pathology meaning I believe the study of disease. So it's a journal. This article is only about linear regression and R squared, but it's being published in a journal that studies, a journal that covers diseases in plants. I think this paper is from 1986. And I mentioned in the introductory level, a lot of the regression methods and statistical methods were developed in the 1800s and early 1900s from the agricultural sciences. And so there's a lot of the early work in statistics and regression was done in agricultural research. And so this is sort of like a assigned reading, and they actually give a lot of example data sets where you should maybe work through some of it. They do several test cases, which you can work through those test cases on your own to try to get a better understanding on the coefficient of determination, or R squared. I believe this paper is available like open source on the internet. Okay, so what is R squared, or the coefficient of determination? It goes by different names. And so this is probably one of the most common and widely used goodness of fit tests. Unfortunately, in many applications, R squared is incorrectly applied and or interpreted wrong by the analyst. And so in many cases, we will use R squared to justify, and perhaps it's the only justification for a bad model. So for example, an overfitting model will generally have a very high R squared. And there are also other circumstances where we chose the wrong model, but we got lucky and it happens to give a large R squared value. So one thing is, overfitting is almost like, it's called an act of commission. We generally, like, the overfitting is usually our fault because we've made a much too complex model, too many regression functions. And there are so many other ways to test for overfitting. And so, but sometimes we make a guess on what the model is, and we get lucky that it happens to fit our data set well. On the other hand, sometimes they will reject a good or correct model in the presence of noise or random error. And so we do a regression, maybe we do a simple regression, line of best fit. And we get a very low R squared, we say, oh, that's a bad model. The R squared is too low, so then we'll fit a high order polynomial that's overfitting, we get a high R squared, then we go with the overfit model. And so yeah, so a lot of times with an overfit model, usually it's a much simpler model is the correct model. So you end up, you reject, using R squared, you can reject the correct model, and then you use it to justify the wrong model. And also, which I've personally seen in PhD dissertations that use regression, and also in journal papers that I've been a peer reviewer on, and also just I consume a lot of journal papers that use regressions. I've noticed that there's a lot of the R squared, you will motivate the removal of data points, which are usually outliers, to achieve a higher R squared. So people remove data points that you should I think I said this several times, I'll keep stressing this, you only remove a data point from your data set if it's not a true member of the population under study, or two, there's an identifiable corruption in the data. So some sort of transcription error, or you know that that set of measurements had the measurement equipment was broken, we determined that after the fact. And so outliers are part of the population. Okay, Olympic athletes, Albert Einstein, the very amazing singers, people who are extremely talented. These are outliers. Or also, on the other hand, people who are terrible. Okay, dictators that have killed tens of millions of their own population. But these are outliers in the population. But their extreme outliers are extremely important to our existence, okay? And so outliers are part of the population. Do not remove them. But researchers will remove data points to achieve a higher R squared, and then they stop with their analysis of their regression model. And so in the practical scientific and engineering uncertainty analyses, R squared has minimal value by itself. Once again, it's just a number, and it's a rather simple number as well. But it can provide insight if used with other goodness of fit measures. And so this is the problem. Most regressions will only use R squared as the only goodness of fit test, and then, well, we're finished, we're done. No, by itself, it is useless. In fact, might give you the wrong impression of the quality of your model. But it's one of these metrics that we use with all of the others. And by the way, residual analysis should be done before R squared. Well, you never R squared by itself you cannot use R squared by itself to justify a model. Okay, so what is R squared? So first is our residual sum of squares, which we first defined in the derivation of the least squares regression. Linear least squares regression minimizes the residual sum of squares function. And remember, sometimes we will use a regression function to evaluate an input point we call the output y hat. And so the total, this is the residual sum of squares is yi minus y hat, which we use that in our residual analysis. And then we have the total sum of squares is yi minus the mean of the sample y's, and then squared in the sum. And so remember, total sum of squares is proportional to the sample variance. And sometimes we call that sum of squares of y in the linear least model derivation. And now we have the regression sum of squares, so the SS of regression. So this is summation of the model prediction y hat minus y bar, so y bar is the mean of the sample output data, and then this is the y hat, the regression function evaluated at the input of each each data point. And so the coefficient of determination, which we usually call it R squared, equals 1 minus the residual sum of squares divided by the total sum of squares. So I'll give you a moment to finish writing all of this down. And so in more of an expanded form, so residual sum of squares is 1 minus, R squared is 1 minus the residual sum of squares divided by the total sum of squares, and then here's the actual expanded version. And so if you go into the textbooks or some of the papers, you'll often see this is the qualitative definition or an interpretation of R squared. So R squared is the proportion or fraction of the observed variation in dependent variable y that can be accounted for or explained by the independent variables x through the regression functions. And so if we just look at our y values, we can calculate the mean of the y and the variance of y. That variance if we account for the independent variables, the regression will account for a fraction of that total variance. And remember that, so the value of r squared that you calculate is conditional on the subjective choice of the regression function and the data set. And so if you are the person conducting the experiment, you usually get to choose which values of xi. Okay, actually your value, when you perform the experiment, you will vary xi. Usually we get to choose, not always, but if it's a well-controlled experiment, we can choose which xi's to execute the experiment or the computer simulation at. And then, which is a subjective choice. Now there's different ways of doing it. You can do random sampling of the input space using a Latin hypercube sampling, or you could use a structured grid. You know, there's different, but all of those are subjective choices. That's actually a whole nother topic we might do in another course, is how should you pick your xi's in your experiment to help facilitate the construction of the regression model. That's that's called experimental design, or design of computer experiments. That's a whole nother field that's closely related. So there's ways to pick your inputs that makes the regression more robust, and ways you can draw stronger conclusions from your regression model. Also then, the underlying functional form you choose in your regression model, the structure of the regression functions themselves. Are you going to use a Fourier series using the expansion of the sine functions, or are you going to use a low order polynomial fit? Those are all subjective choices. And r squared tells us nothing about the unobserved values of y, i.e. model prediction. R squared does not give us any information about the accuracy of model prediction, which is usually what we're interested in. We want to use this regression model to make predictions, either interpolating or, in some cases, if we have confidence in the model, extrapolating. So the r squared tells us nothing about the unobserved y's, so model in prediction mode, or the true underlying functional form of the physics of the y-x relationship. R squared only tells us about the subjective choices of these xi's and then this model structure to the observed yi's. And so if the chosen regression functions happens to accurately describe the underlying physics, then the r squared tells us about or quantifies the random noise present in the data set. So this is a special case. So if we have a priori knowledge of the underlying physics and we incorporate that into the model, so we know we have the correct functional form, then on that special case, then r squared actually helps us quantify the noise, basically the variance of the noise, or the standard deviation of the noise present in our model. Okay, and we already had, this is the previous definition of r squared. We can also, generally for the linear regression models, the regression sum of squares, the residual sum of squares plus the regression sum of squares equals the total sum of squares. And so then we can write r squared equals the sum of squares of regression divided by the total sum of squares. And so, for linear models, and this is for linear models where you solve for your coefficient using least squares regression, that's using just ordinary least squares, r squared will always be restricted between 0 and 1. So yeah, this relationship is for linear models, okay? Linear in coefficients that are solved using least squares regression algorithm. There are other algorithms like weighted least squares. There's other ways of doing the parameter estimation where it won't be restricted between 0 and 1. But so for a linear linear and coefficients model solved by ordinary least squares, this will generally hold. But that's the thing, so for some of these other more exotic regression methods, they might have like modified definitions of R squared. So just be aware that, once again, if you're using third-party software and they're calculating R squared, you should know exactly how they're calculating it. But we're going to discuss it in the context of linear regression. And so, generally, I consider R squared a bad metric for goodness of fit. In fact, I usually think it's a terrible method because I have experienced more often than not that it's misapplied and it's uses to justify a bad model or to eliminate a good model. And so first, why do I consider R squared a bad metric? And so first, if R squared is large, let's say approximately equal to 1 or greater than 0.9, most people will assume the fit is good. And so then we got to ask, what can cause a large R squared value? And so first, if the model fits the data very well, the residual sum of squares, which is the numerator, so it's 1 minus some fraction. And so the residual sum of squares approaches 0. And we saw that in our sine example using the 22nd order polynomial. The residual sum of squares was a really small number, almost 1. I think it was around like 0.1 to 0.15. And so when the model fits the data very well, this term goes to 0, which means R squared goes to 1. It means this fraction goes to 0 and R squared goes to 1. And there are two reasons for a good fit. One is the correct functional form of the model was chosen and the data set has small noise. 2, which is the more common situation, a complicated model with too many predictors or regression functions was selected. Basically, you have the wrong functional form and then the overfitting gives the small residual sum of squares. And so condition 1 requires basically luck. You have to either guess lucky or have you're lucky enough to have the a priori knowledge of the physics, and your experiment has very small noise. And then of course, overfitting is terrible. I think we saw that in some of the residual analysis. And we have to avoid overfitting because an overfit model is not only it's not a worthless model, it will destroy your analysis. And so 1 requires luck, 2 must be avoided. Okay, so now let's look at the other situation. If R squared is a small value, most analysts will assume that it's because it's a bad fit. Well, let's ask ourselves, what can cause a small R squared value? Once again, here's our equation. It's 1 minus this ratio. So remember, the most simple model that can be assumed is that there is no functional relationship between the input and output. Basically, we assume that y equals the sample mean. So this is actually the 0th order polynomial fit. So the least squares regression will give f of xi equals beta naught, which equals y bar, the sample mean of the output. So if there is no input-output relationship, least squares regression generally will return the uninformative model, which is just the sample mean everywhere for the whole input space. So in this situation, and so we substitute in y bar. The numerator and the denominator now are equal. That goes to 1. And so 1 minus 1 is 0. So sometimes, and actually this happens especially in the social sciences where you might be studying, for example, human behavior. And so is human, especially for example in advertising, they do all sorts of experiments. Okay, will the human behavior be affected by variable X? Or will the probability of a person buying the product be influenced by variable X2? And so 90% of the time, actually, we are not influenced by certain now, there are certain variables that are very influential in advertising, but many of them are, a majority of the time, your experiment and regression analysis will confirm that there is no relationship, and that's okay. If there isn't a relationship, we need to know that. And so, if the regression actually gives the sample mean that the R-squared is 0, but a lot of the times the regression will correctly identify there is no correlation between the input and output, okay? And so for example, let's say we do a study where we measure the first 100 people that walk by us, we measure their weight and ask them for their date of the birthday. And so do you think there would be a correlation between the person's weight and then the second digit of the day in the birthday? So for example, January 3rd, 1985. That actually happens to be my birthday. Or September 17, 2001. So do you think, so my digit would be 3, the other person's 7. Do you think there's a correlation between our weights? And let's say we did this for 100, 200 people. There's probably going to be no correlation. Now we might get lucky that in the sample size we have, there's probably no correlation. And so we would hope the regression would show that, and our R-squared would go to 0. And so in this case, sometimes if there is no correlation and the regression accurately determines that, R-squared will be 0. So some cases the correct model, and actually many times in many fields of study, there is no correlation, especially, for example, drug trials for treating certain diseases. There's hundreds, if not thousands, of drug trials going on right now, and you always test against the placebo. The placebo is usually just a sugar pill. And so most drugs, there are thousands. You go onto the stock market, you can probably find in different, the New York Stock Exchange, probably the Korean Stock Exchange, there are hundreds of drug companies. They're usually small companies. They all have drugs in certain trials. They're treating all sorts of diseases. And so, but most of the time, the majority of the, not the majority, but the vast majority of the time, probably greater than, I don't know the exact statistic, I wouldn't be surprised if more than 95% of drugs that enter trials end up being either they don't treat the disease, the targeted disease, or they might actually be more harmful than the disease it's trying to treat. And so probably most of the time they don't work at all. And then, you need to know, and the earlier you can find that out in these drug trials, the better, because then you can move on maybe to a new idea that actually might have a chance of treating the disease and saving people's lives or improving their quality of life. Yeah, and so in certain, especially in certain fields, most of the time you will not find the functional relationship. In that case, the R-squared will tend to be much lower, and that's actually correct. And also, even if there is a strong relationship between the inputs and outputs, the random noise in the data leads to large total sum of square terms. Okay? So, in the denominator and also the large residual sum of squares in the numerator. So, especially if you have large random noises, the more noise you have, this term becomes a large number, and naturally this term will also be a large number. So a large number divided by a large number is approximately 1, and then so this is the R-squared will tend to be small. And so even if you assume the correct underlying functional form, R-squared will be small despite having the correct model. And so the key takeaway, R-squared only measures the model fit to the data, no information about the data noise, and indication if the model is correct. But if you do have a priori knowledge of the underlying form, of the underlying physics, and you implemented that in your model, then it will give you a measurement of the noise. Okay, so let's move back to some examples. This is our first really simple model. We did the 1.5x. So remember, this is our original data set, and we have the two correlated inputs with correlated noise. And here, so whenever you do a regression, you always need to provide the regression equation and then r squared. So even though I personally think r squared is almost useless, you still need to provide r squared on your actual plot. Like if you submit to the journal, you should have the regression function and r squared displayed on the plot or in the caption or discussed in the text. Ideally in the legend of the plot. And so here we have our 5 data points, r squared is 0.96. Okay, so hey, even though, that's the thing, 0.96, that's a really high, that's almost 1. Forget about just looking at r squared, oh, that's a good model, but 1.2 versus 1.5 for slope. And so our model is actually off for the slope variable, the model is off by, about 20%. So is a 20% error, would you call that good? And so, 20%, that usually means pretty significant. But r squared is indicating a good fit. Well, it's these 1, 2, 3, 4, these 5 data points are fitted by that particular line quite well. But it doesn't tell us anything about how accurate is this function to the true underlying function. And so let's add more data points. So always in regression, the more data points we can provide to the regression, the better. And so here we go to this is the same data sets I showed in the lecture 4, I think this would be lecture 4.1. And we've looked at it in the residual analysis as well. So let's add data points. So now we have 25 data points. Our actual regression function now it's 1.4. It has a really small 0.03 y-intercept. Also our y-intercept has some error, 0.2 versus 0. We can't say what percent it is different because 0, you can't do it relative to 0, a percentage change relative to 0. But this is 1.4x plus 0.038. This is a much closer representation to the true underlying function. So it's actually a better fit to the true, it's a better estimate of the true underlying function. But r squared is 0.957 versus 0.96. So it's actually a better estimate of the true underlying function, but actually has a slightly smaller r squared. Now, of course, 0.96 versus 0.95, you can't make a comparison. Also, you never compare an r squared for 2 different data sets. Now, the same data fit with different regression models, you can then compare or rank the r squared. It's entirely inappropriate. You can never say, well, this model is a better model. These are 2 different data sets. So it's meaningless to do cross comparisons of r squared between 2 different data sets. Now let's say we try to fit a quadratic to here, then to the same data set, we can compare the r squared. But and by the way, 0.95 and 0.96, that's trivial. So now let's go to the 250 data point case. And so here now we're converging onto the actual true solution. But look, 0.952. So this is actually the best regression. We have the most data. Our regression function actually almost matches the underlying function, yet it has the smallest r squared. Of course, the difference is trivial, okay, less than 1% difference, but the best model with the best data, the best training data set has the smallest r squared. Now this is the data set where we uniformly sampled between 5 points between 0 and 1. So here, r squared is 0.98 for our 5 data point set. This model, 0.93. Now we have, see, we added 25 data points. The actual functional fit is much closer, but look, we went from 0.98 to 0.93. 0.98 to 0.938. This is actually a measurable decrease in r squared, yet we have more data and the actual fit is actually a better estimate. Now let's also go to the 250 data point case. We have a really good estimate of the true underlying function, but r squared is 0.95. So both of these cases significantly less than that R squared. We also did the cases where we did the 250 data points, but our random noise variance is 0.25, or a standard deviation of 0.5. And so here, both of these models, we're doing this line of best fit. Both are good estimates of the true underlying function, but look, R squared is 0.49, R squared here is 0.41. Probably the majority, more than 50% of analysts would say this is a bad model. But first of all, the linear function is the true underlying function, and we have large noise variance. We have constant noise with a constant variance, and that variance is large. So now this is telling, this 0.41 and 0.49 number, it's not telling us about the model fit, it's telling us about that the noise, the variance, the standard deviation of the noise is large relative to the range of our y value. Now, if the equation was y equals 150 times x, and we have the same noise, then R squared, now R squared would be like 0.98. And so it's the standard deviation of the noise is large or comparable to the range of y values. That will give you a very small R squared, despite having the correct functional form, the correct model. And so in this case, these low R squares are telling us about the magnitude of the noise relative to the y value. So it's the noise to signal ratio, or signal to noise ratio. So if you have the correct model, R squared gives you a quantitative measure of the signal to noise ratio. Okay, and so now let's look at our sine example with all these different polynomial fits. Remember we already showed these plots in the other previous lecture. Let's look at our models here. And so here, this is the y equals beta naught, or beta 1 sine of x plus beta naught. This is the correct underlying form. It's R squared is 0.77. And by just looking at the fit, we know that that's a good fit, even if we didn't know about the underlying form. But R squared 0.77, that's too small. This is the hybrid model. It's the sine function plus a linear model. That we get qualitatively the same fit, but R squared is now 0.78. So we've had like a 1% increase in R squared. But really, this model is just fine. Now this is that other hybrid model, the sine function plus the cubic. Remember, the cubic function was also a very good fit, just from our visual inspection. And so now here, R squared here is 0.80, a little bit higher. So all three of these models are good fits, but we would probably end up going with this one. This is probably the most simple model. The more regression functions you add, a little bit more flexibility in the regression fit. So the more, basically these are like degrees of freedom in the regression. The more degrees of freedom we have, that will tend to increase R squared. And so the fact that R squared has not changed by very much, it's basically a it's a trivial rounding error. We can't really say that without any other information, all of these models are equivalent in terms of the fit to this data. But generally, you would want to penalize these two models because they have more number of regression functions. So you have to give extra points if you have a model that's a more simple model and it performs well. Generally, that's probably the better model than a more complex model that has similar performance. And so what are the key takeaways for R squared? R squared is the most commonly used statistical test for the goodness of fit, but in practice, R squared does not provide us with the useful information about the goodness of fit. R squared should still be calculated and presented with the regression equation on your plot. If now, in the special case where you do have the correct model that's been selected, and the noise is constant and independent of the predictors, so it's constant variance, R squared gives you a quantitative measure of the noise variance, or and really the signal to noise ratio. And And just to remind you, with this, there's required reading this paper, and they actually have some nice test cases. If you don't believe what I just, probably all of you have heard of R squared before, even maybe have calculated R squared for your line of best fits in maybe undergraduate courses. They actually have some interesting test examples that you can work through. And so along with the required reading, that journal paper, you have a programming assignment. I want you to calculate R squared for the y equals 2.5 sine of x problem data set that you've already been doing for your residual analysis. So calculate R squared for the simple linear, quadratic, and the cubic fits, plus the exact function and the hybrid model fits. So I didn't show you the actual R squared for the simple linear, quadratic, and cubic fits on purpose. I want you to do that yourself, and then you can check in the lecture, also do it for the exact function. I provide that on the slide a few slides previous. And so here, once again, here are your residual, your coefficient of determination or R squared equations. All right, and that's it for this lecture.